All right, everybody shut up! It's like my coin phrase. Was it this group or was it another group? Another group a while ago, they made an Android app that was like a soundboard of like Lippmann sayings. They were going around the dorms. You guys hear about this or knew about this or? So, you're playing it in the dorms?
They put on GitHub at least?
I mean, do you know how much that hurts my feelings? Oh, I do have something to report that does hurt my feelings. And it involves this class from like three or 4 years ago. Okay, and it also involves you whining about not spending too much time on your homework. Okay, so I'm dropping names here because I'm mad. Okay. How many of you know Annalise Promchinsky? Yeah. All right. So when she took this class many years ago, 3 years ago, 2 years ago, something like that, because she's one of my grad students now. The end of the semester, they were in the study group, really diligent students, worked hard, blah, blah, blah. That reminds me, if you're not working in study groups, get in study groups, especially as we start getting into these assignments, because you think this one was hard, this one's trivial, this assignment. Next one is going to be just impossible. But in any case, on the day of the exam, they brought me a present. And it was one of the best things I've ever received. You maybe have seen it hanging in my office. They brought me this necklace with these little vials on it. And they were vials of their tears. From studying for this exam. Okay? So at the level that you know me now, like, you could imagine how I would appreciate that, right?
What did you do to the exam?
This is before the exam. This was them preparing for the exam. They gave me the vial, they collected their own tears and presented them to me as an offering prior to the exam. And just this Tuesday night, years later, I find out they were not real tears. Coburg faucet water. That they had to keep refilling because the cork on the little vials was turning it yellow. To go for 3 years believing your students actually gave you their tears and then to be hit with that reality.
That's what I thought too. Oh my God.
I mean, human misery is one of my hobbies. Okay, so you can imagine how touched I was from a gift like that, right? And now to find out now. Can you imagine what the rest of her semester in this grad class is going to be like with me? Unfortunately, I can't give different assignments to different students, so the whole class is getting just train rolled. Oh my gosh! All right. Yeah, so vials of tears is good. Oh, I've had videos, pictures are fine, videos are better, of students actually crying while working on homework.
I can just buy 2 drops.
That is bonus points. Okay, like if you submit with your homework, like, okay, look, I've worked really hard on this, spent 12 hours, and it doesn't quite work. And then you also have like a link to a YouTube video of you just bawling your eyes out. That is like 20% bonus. Okay.
You could just buy some like teardrops and record. That's
Yeah, if you're gonna do that, you gotta sell it. If you can't force yourself to cry from one of my assignments, then the assignment wasn't hard enough. Is the point, right? I did make a mistake many years ago, where I made one of these comments like this, like, oh well, if you do this, I'll give you some extra credit. And I may have told you this before, but it was around the final exam. And I said something along the lines of, oh, if you sign your name in blood.
Oh my God.
I had a student come up, wanted to make sure it was fresh. Got his hand and signed his exam right now. I had to wait for his exam to dry.
Oh my God. Yeah. That's so crazy.
So use your best judgment when you're deciding when I'm kidding and when. Luckily, he wrote a very solid exam, so I didn't have to be unethical in order to deliver on the promise. But reminder, tonight, 7 p.m. across the hall in the Fishbowl, we're with the Grace Students Computer Science group thingy. We're watching Hidden Figures movie, really good movie. If you haven't seen it, it's about some African-American women who were working for NSA and NASA kind of at the kind of the same time, doing a whole bunch of math computation. So women in the early days of computer science, they got this big computer in there, and only these women knew how to run it. The high-powered men that worked there, they didn't know what to do. But so it's kind of a mixture of early women pioneers in computer science, and then also some racism type stuff where they had to use separate bathrooms and things like that. So you kind of get the feel for the unfairness and things like that in there. But it's a really good movie. If you haven't seen it, stop by. Even if you can't be there for the whole movie, it's 2 hours long. Still stop by. We're going to have some snacks and stuff, but we'll be watching it on the big screen here over in the Fishbowl 109. Cool? So that's tonight at 7 p.m. All right. So let's look at this easy assignment. So you were supposed to write AddEnd, right? For this assignment. So AddEnd means, so let's just write it real quick and then we'll explain it. All right, so we're going to say AddEnd int value. We'll say if this dot head is equal to null. If we're dealing with the empty list, we'll just call add front, pass to the value. That part makes sense? If I don't have anything in my list, I already wrote add front. So adding front, adding end, same thing. I'll just have add front. Go ahead and do the adding. Okay, otherwise I have something in my list. So I have at least one node. So I need to move to the last node in the list. So we'll call this guy KerrNode. We'll start him equal to this dot head, while KerrNode dot get next node is not equal to null. KerrNode equals KerrNode dot get next node. And then we'll go ahead and create our new node that we're adding, and we'll say KerrNode dot set next node to n. That's it. So we will, this code right here starts off a pointer at the beginning of the list, pointing at the front of the list, because we don't want to change head, because head keeps track of where the beginning of the list is all the time. So right here I'm saying I'm going to have something point to the same place as head is pointing to. Let's draw this picture here. It's not this class, right? What class is this? This one? Okay, so if I have my linked list that looks like this, and then I call, I'll move this guy up here, so I can just put another line here, and I say ll.AddEnd, we'll add a 3 to this guy. All right, so what's going to get created here is I'm going to get a brand new node that's just floating out here. This is my n that I created here, right? That's this line right here. Just that line. New node. All right. Now I'm going to have a variable. We'll call this guy KerrNode. All right. And we're going to start him off at the same place. He points to the same thing that head points to. Make sense? Okay, so they both point to the same place. So far, so good? So that's what this line right here does. Then I have a while loop. Now, when do we use while loops? So we have a bunch of different kinds of loops. When do we use for loops? What kind of problems are for loops kind of built for?
How many counts?
Yeah, counting type problems, when we know how many times we need to spin through it. Okay, so while loops are loops. They are still pre-check loops, so there's no guarantee we get into the body even once, but they're kind of built for when we do not know how many times we need to spin through our loop. So we're going to say, while this Boolean expression is true, that is, I take KerrNode, I ask him for his next node. So as long as his next node is something other than null, which means he points to another guy, which means he's not the end of the list. So right here, right off the bat, KerrNode is right here. Does KerrNode's next node point to something real or point to nothing?
Something real.
Something real. Okay, so KerrNode's next node, this is KerrNode right here. His next node is actually this node right here. So I get into the while loop, and I set KerrNode equal to his own next node. And what does that do? That does this. Makes him point to his own next node. Then we loop back up. We say, is KerrNode's next node, which is this dude right here, is that equal to null? Nope, that's a real thing, right? So we get into the body of the loop. We set KerrNode equal to KerrNode's next node. Loop back up. We ask the question, is KerrNode's next node, does it point to something real? Or does it point out to space? Now it points out to space, right? So this guy's next node is set to null. Remember that when nodes are first born, here's my node class, we set the next node, we default it to null. And only when we explicitly call set next node does it get set to something other than null. All right? So at this point, KerrNode is pointing at this node. We've spun back up on the loop. We're asking the question, is this guy's next node something other than null? It's not, because it is null. So I fail that Boolean expression, fall past the end of the loop. So that puts me right here. That's actually the point in time when I created my node n. So that's when I built this dude. And then what's the thing I do? I set KerrNode's next node equal to that end. So I'm going to take KerrNode points here. I'm going to set that dude's next node to that.
Okay. So what is the difference between when you set the next node and when you make something equal to, like n equal to head, and then like using the next node? Like I don't get the point of like the pointer thing. It's really confusing to me.
Okay, I get what you're saying.
Like that one is still pointing to the next, and now you just point the other one. You know what I'm saying?
Yeah. So this guy used to do this. It used to look like that, right? Pointed nowhere. So this KerrNode is a variable. What are variables? If you had to give me a concise definition of a variable, what would you say? Place to store stuff. Okay. Now, Java is a strongly typed language, correct? Mm-hmm. All right. So, what does that mean for a language to be a strongly typed language? We have to define them specifically for the types of values we're going to hold in them, right? So, if I come back here into the code, I created KerrNode here. What kind of value is KerrNode? It's a node. So when I store something inside of KerrNode, if I were to peek inside of this box, what would I see in there?
Two fields.
What does that mean?
This is a variable, right? This guy's a variable. Variables have values. All right? If I were to, and we set this guy's value equal to this dot head. Okay, so I gave him a value. His value is, you said it's a node, you said it's two values.
Yeah.
Tell me why both of you were wrong.
It's pointing to memory address.
Yeah, the value in here is an address. I did create a node. This address right here currently points to, in our code right now, that actual node. Here is the real node that lives somewhere in our computer's memory. KerrNode does not hold the node itself. It holds the address where that node lives. All right, this goes back to if you're having a party at your house and you were inviting your best friend, favorite teacher, okay, Mike, to your party, then at 8 p.m., you don't tell me to just open the door to the house because you've handed me the house and I've been sitting there holding it all day. You've given me a little tiny piece of paper that says where I can find the house. That's what KerrNode is. KerrNode holds a memory address of where I can find that node inside of memory. Right.
Okay, how do you know that the up node is not holding an address and the other one holding an address?
What do you mean? How do I know this guy is not holding an address?
Yeah.
Well, because if I gave you a piece of paper with the address to my house, how do you know that that guy holds an address and my house is the actual house? So I'm asking the real life version of the question you just asked. Well, you can definitely tell the difference, right? You can tell the difference between the piece of paper that has my address on it and if you're standing in my driveway looking at my house.
Mm-hmm.
Like those are two clearly different things, right? Okay. Now, somewhere, right down here, this is when we use the constructor, right? This is our call to the constructor for node. And we built an actual node. This in my examples here, this is where we actually built the house. Make sense? What does the new keyword do? That's our real estate agent. Okay. And what do real estate agents do in Java? Find some memory, find a nice plot of land inside of memory for us to go ahead and toss this house, toss this node. So we're actually going to build that node somewhere out here in memory at an actual real estate location. But what the new keyword does is it returns the memory address where you can find that. Okay? And I'm storing that memory address in this variable here called n. That make sense? Okay, so now where I think you're getting hung. So does that part make sense, what I've said so far? Okay. So now I'm going to show you something else. I'm going to say int a is equal to 5. Then I'm going to say int b is equal to a. What value is stored inside of a? It's a integer literal, 5, right? Not a memory address, not a string, not a char, not a Boolean. It's an int. That's the kind of value this guy was built to hold. So his value is 5. Now if I say I'm going to create another variable called int b, I'm going to set that equal to the value of a. That's what happens here, right? We resolve a to its value. What's a's value? 5. So what am I putting in b? Putting it in 5. So after this line of code, a is equal to 5, and b is also equal to 5. B, now, if I then come and do this, if I say a plus plus, did the value of b change?
No.
Value of b did not change. A is now a 6, but because I copied a's value into this other variable called b, that had no impact on b. B is still the number 5 because that's when I put the value in there, that's what it was. And a has now become a 6 because I changed it. Do those 3 lines make sense? Okay. So if this dot head up here, when I first built this linked list, it started off as a null value and then presumably had some node attached to it. So that guy holds, what kind of value does this dot head hold? This dot head is a variable capable of holding a node. So what kind of value lives inside of head?
Address?
A pointer to a node. Integers it is an address. When I say pointer, I'm talking about it's an address that points to where the thing actually is. If I handed you a piece of paper with my home address on it, that is pointing you to where my actual house is. Make sense? So when I have variables whose types are objects, let's say with the exception of strings. Strings are a little bit more mysterious, but every other kind of object, all right? What I'm actually doing is I'm holding a container here. I have a container built for holding a memory address that will ultimately point to where that object was built in memory. That make sense? So this dot head holds some memory address. Now when I'm creating a brand new variable here called KerrNode, that's of type node, what kind of value is this bucket built to hold? It's built to hold a memory address, right? Because this guy is a variable of type node object, and object variables hold memory addresses which point to where that actual guy lives in memory. And I'm setting KerrNode's value equal to the same value that's in head.
So is that going to be null?
That's the same, well, it's going to be whatever the current value of head is.
Oh, okay.
It could be null if it was the very first time through, or it could be some node in memory, right? It's whatever that value resolves to. So this line right here is identical to this line right here. But we're more comfortable with this line because memory is scary. Right? That's why the assignment took you so long. You saw the solution. The solution's not very long, right? And even when we go through the picture wasn't all that scary. But as we were dragging pointers around, as this guy started off, this is when I say KerrNode is equal to head. That this guy has the same value as this guy, which means that the address they hold both point to the same place. And then what did I do to KerrNode? I took him on a voyage. I traversed my list until I got to the end of the list. Once I was at the end of the list, I set the current end of the list to point to my new end of the list. Make sense? All right, so let me get rid of these couple of things here. So there's our solution.
Question.
Mm-hmm.
Can you so then like still the question that like point thing. So like how is that point of KerrNode makes the thing up there connect to the other?
Okay, so if I started off here and I have KerrNode equal to the same thing that head is equal to.
So
That means both of these guys hold a value. That value is a memory address. That memory address points to the same space in memory. Okay? Then I ask the question. So my while loop says, while KerrNode's next node. So when I say KerrNode's next node, I am actually, so KerrNode points to an actual node in space. And I'm asking that actual node, that instance of a node, to call his instance method called getNextNode. And I'm saying, is your next node, so that's where I have this pointer here, right? So here's an actual node. If we go back and look at the node class, a node has a private field called nextNode. What kind of value is nextNode built for holding? Memory address. All right, so I'm asking that dude. So when I say KerrNode.getNextNode, I am resolving KerrNode to hit the actual node object that he points to. So KerrNode becomes this actual node. I'm saying I want to get your next node, which is going to be the address which points to this guy. Okay, but I'm getting the address, and I'm saying, is that address something, or is it currently nothing? Okay, null means nothing. And if you look at our starting point for a node, when we first construct a node. What do? All nodes are born with a next node that points nowhere because we have not connected them up yet. You know, it's like you dumped out the box of Legos, and until you start building your castle, the Legos, they don't have a home, right? Make sense? Nothing points to that Lego. The Lego doesn't point anywhere else. It's kind of it's an awesome example, I think. All right, so in my while loop here, I'm saying, get me the node. When I resolve, I'm using the value that's in KerrNode now, right? That guy will resolve to his memory address, which will kind of zip me to that address in memory and say, found a node. Okay, presuming he actually is equal to something. I wouldn't be in here if KerrNode wasn't a real thing. That's what this else is about. Because KerrNode starts off as being equal to head, right? That's what I did right here. I'm only at this code here if head was something real, something that was not equal to null. All right, so if head is something real, I'm going to make KerrNode point to the same thing as head. And the whole reason for that is never, ever, 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 ever change the value of head and lose the front of the list. Okay, we're gonna write remove front here in a few minutes, and we will have to change the value of head in remove front, but we'll have to be very careful not to lose the old front of the list so that we have a value to return or something like that. Okay, so this guy right here says I've provided myself a variable that I can use to skip down the list without impacting head at all. So each time through, I'm saying, get me the actual node that lives at that memory address. Ask that actual node to provide me, so that's an actual node, which is an instance of the node class. I'm asking that actual instance of the node class to call his getNextNode method. Okay? How do you know this guy's a method? Parentheses. How do you know that guy's an instance method? Okay, because I'm calling it with an instance of a class. In this case, I'm calling it with an instance of the node class. All right, so if I go and look at my node class, would I expect to find static before this guy, or would I expect to not find static before that guy? Not static. So we'll go into we're already at the code. Here is getNextNode. And we do not have a static in front of it, which means that guy is an instance method. So the proper way to call that guy is with an instance of the class in which the method was defined. This guy was defined inside of a class called node, so I need an instance of node in order to call that getNextNode method. And right here, I have an instance of node. So I'm asking that actual node to provide for me his next node variable, the value that his next node variable contains. So here's his next node function. This guy returns a what? A node, memory address that points to a node.
Yeah.
Yep. So that's the nuance, right? That's the challenge right now. We're so used to not actually thinking about memory and just letting our language magically do this for us. And part of that is because we've learned languages that have not forced us to do memory. It's always just been managed for us. But now we're like, you know what? That old management style, while good sometimes, when we know exactly how many elements we want to store and we want to be really, really, really fast, that's no longer good enough. I need to create my own little storage containers now that allow me to arbitrarily change the size of it, right? So that's now we're having to play with memory ourselves. Go ahead.
Question. So when you create like a new node, then does your list like keep track of every single address that you know what I'm saying? Like
The list as a whole doesn't. So if we think about the linked list here, all a linked list knows about is how many total nodes are in there, because we're playing that game. So actually, to fully solve this problem, here's my AddEnd. This dot count plus plus. I have to increment my count because I did actually just add something to the end of the list, right? Why am I not saying this dot count plus plus up here? Yeah, add front. I say count plus plus. Really, it should be this dot count plus plus, but it'll work anyways.
Okay, so it sounds really dumb, but like, how is that count plus plus helping you like keep track of the addresses?
It's not actually helping me keep track of the addresses. It's just letting me know how many total elements I have in my linked list in case I'm interested. Because my linked list looks like this. As a human being, we can glance at this guy and say, there's 4 things in there, right? What we're saying is that our linked list is able to report to us that he stores 4 things. But there's only one other thing that a linked list actually stores. It stores the beginning of that list. So all our linked list knows is how many total things are linked together, because we've written that code, and it knows the front of the list. If I want to get to the next element, I have to start at the front of the list and then traverse the list to get to the second element. If I want to get to the third element, I need to have first gotten to the second element, then I can go to the third element, and then I can go to the fourth element, so on and so forth. So the linked list itself does not know about all the elements. It knows only about the first element, which you can then use to get to the second element, which you can then use to get to the third element, so on and so forth. And that's the power of the linked list from a memory efficiency perspective, because as I added things to my list, I created just enough memory for that value, somewhere in memory. Then I created just enough memory for that value, somewhere in memory, so on and so forth. So those guys did not need to be contiguous. I mean, they're very, very, very likely not contiguous unless just roll the dice luck. The new keyword returned 2 memory addresses right next to each other, but they are not assumed to be contiguous. So that's why I have to walk the list, traverse the list to get there. Go ahead.
Does running through the nodes take a long time? Like, would it make more sense to have, like, track the last node rather than go through the entire node list?
Definitely. So 2 parts to your question. First part, does it take a long time? Yes, that's the linked lists are a relatively slow piece. Now you're saying that it might be convenient if you want to get the first element in the list. We already have a way of getting the first element quickly with head. You're saying it might be convenient to be able to quickly get to the end of the list, right? So a common thing is to have another variable in linked lists called tail. That always points to the last element in the list. And that can be pretty handy because in our code for AddEnd wouldn't require us to dance to the last thing. We already have the last thing. So if we did keep track of tail, let's just let's play that game. So now I'm going to have my linked list. This guy's going to have a private node tail. When the list first comes into existence, tail will equal null. Add front, if it is, if head is equal to null, then actually this is add end. Let's do add front first. Add front, we create our new node. If head is equal to null, head will point to the that new node, and then we'll say this dot tail is the same thing as this dot head. Because now we have a 1 list, so head and tail both point to the same place. Okay? Otherwise, if we're adding to the front of the list, head will update, but tail does not move. Correct? All right. So now tail of the if we are doing our add end, if we say this dot head is equal to null, we'll just call add front. We'll leave that the same. Otherwise, we can go ahead and say node n is equal to new node value. This dot tail is, we'll say this dot tail dot set next node to n. So that will set the current end of the list to, we'll set that guy's next node to my new node. Then I'll say this dot tail is equal to n. I'll point it. So if I happen to keep track of tail, this is the entire solution for AddEnd. Why is that? Because in this particular case, tail already points to where KerrNode ended up pointing to. I could just immediately get to the end of the list using that tail variable. So that could be convenient, right? Now, generally speaking, when you have a tail for on your list, you're typically then thinking about something called a doubly linked list, which means that nodes don't just have next nodes, they also have previous nodes. So that means if I went to the end of the list, I can actually get to this guy here from this guy here. Right now, I can't do that, because right now my nodes only know about next nodes. Does that make sense? Mm-hmm. They only know about next nodes. So given that, if I want to be able to go backwards and forwards through my list, I'd have to add another variable, another field to my node called PrevNode, or something like that, that keeps track of the previous guy. That could be convenient. But the reason why we're not using tail yet is because we're right now trying to practice working through memory. We're kind of dealing with the limitation. You know, we kind of have like a, I don't know, like a weird weight on our left leg or something like that, where we can't quite do everything we really want to do. But you're absolutely right. You're saying, look, getting to the end of the list quickly might be beneficial, especially as you have, as your list get bigger and bigger and bigger and bigger. At that point, if you need to, walk from node to node to node a million times, that will take some time when you could just jump to the end real quick with tail. So I would say that keeping track of tail here like this is not a horrible idea, even if you weren't going to do a doubly linked list. But just to keep things complicated, we're not going to keep track of tail in our linked list currently. Okay, instead, right here, I am calculating tail. I start at the front of the list and I run to the last element of the list. That's effectively what that code I have highlighted right there does. It gets me to the last node of my list. It gets me the value that I would ultimately have if I were keeping track of the end of the list. You don't get which part? What this code does?
No, just pull back your picture. Sorry. Okay, so like the KerrNode.
Yep.
KerrNode, so you put it to the next, right?
Yep, so KerrNode
Like
starts off
seven
here.
next, like the one
Does
that
this guy
we
have a
have.
next node? Yes, go here. Does this guy have a next node? Yes, go here. Does this guy have a next node? Yes,
So
go here.
Give me a second, just stop right
Okay.
there. So then you said the KerrNode set to the next node. I was just really like curious of like how is the 7 next connected to the 3 next, because you just have the KerrNode connect to the 3 but not the 7 to the 3.
That's
And then
this
you
variable right here. Nodes keep track of the next node. So
It's
when,
automatically connected.
well, I connected it. So this last time through, when I added something to my linked list, I said, current end of the list, set your next node to n. At that point, we set the previous end of the list's next node. So that's what set next node does. Set next node takes in a pointer to the next node and sets that guy's next node equal to that pointer. That's how we hook it up. So every node knows about the next guy right now. So if you're at the beginning of the list, which is this dot head, he knows about guy at position 1. If you're at guy at position 1, he knows about guy at position 2, who knows about guy at position 3, who knows about guy at position 4, because when they were eventually added to their list, we let him know about the next guy. So if you're currently at the end of the list, okay, this guy is like lonely, right? He's standing out here. There's stuff that point to him. He doesn't know that. People are kind of staring at him, right? But he's just standing out there in the void. He's got no friends, because he's just pointing to nowhere. Make sense? Only when we go to add a new guy onto the end of the list does he get a buddy. At that point in time, he'll point to somebody else, who now is the new lonely guy. Make some sense? All right, so in our current implementation, we are not going to use tail. Although I would say that efficient linked lists would typically use tail. Makes sense. Wasn't that hard to keep track of the front and the end of the linked list, and that could save you some time to quickly zip to the end of the list. So, yeah, that's a kind of a more optimized linked list. And then pretty soon here, probably for your next homework assignment, you're going to just be pining for that previous node. It's like, man, it'd be so good if we had the previous node, but we don't. That's the problem. So, which is fun, yeah. All right, so let's now, I suppose we can officially test our linked list here. Let me make sure I've removed my tail from all the places. Okay, we look like we're good. I was testing it in main activity, right? Yeah, so here's my linked list. I have a couple of add fronts, and I'll say ll.addEnd, and I'll add a 3 there at the end. So we should get a 2, a 7, then a 3. We'll tell that guy to display itself. Where's my... There's my 2, my 7, and my 3. So we've tested it against, and then if we really wanted to, maybe the first time through, we can, instead of adding front, we'll add end the 7, which notices that where we have the empty list and just calls add front internally. So if somebody happens to add something to the end of an empty list, it'll still work because we actually wrote that in terms of add front. So we'll see that this still works. Oh, I wonder what that guy does. Like a little lightning bolt guy? What does he do? Apply changes? Oh, okay. So there's our other 273. All right, still works. We're good. All right, so I think at this point we have verbosely tested AddEnd on every possible permutation of testing. It never breaks. It's fine. All right. So what else might we want to do with a linked list? We are thinking about linked lists as kind of alternatives to arrays. Not necessarily better or worse, just alternatives. Arrays let us store stuff, right? And we can certainly sort of kind of add front and sort of kind of add end to an array if we wanted to, but typically we just fill arrays up with stuff. But the main function of an array is to be able to get a value from a particular bucket in the array. All right, so maybe like, get at index, like give me the value at bucket 4. Give me the value at bucket 5, something like that. So we're going to write a function here inside of linked list public, and we have a couple of options here. We can say we're going to hand you the node that has the value in it that you can then extract. But realistically speaking, if you are asking for whatever's at bucket 4 in a linked list, what you actually care about is the payload, the value that lived in that node, right? Okay, so rather than this guy returning a node, we're going to have it return an int, which is the payload type for our linked list. All right, and we'll call this guy get at index, and he'll take in an int index. All right. Now, whatever index is, for right now, we can assume that it's a legal index. We don't need to do the error checking on it right now, just because we're wanting to focus on the memory stepping stuff. All right, so if I want to get bucket 0 or bucket 1 or bucket 2, how do I get that value at a particular index here?
Go through the list until you find the node with that number.
Okay, how many steps do I need to take in my list?
That is like how many it needs until it gets there.
If I want bucket 0 here, am I going to start off probably with something like KerrNode pointing at this guy? And if I take 0 steps, am I at bucket 0?
Yeah.
If I took 1 step, am I at bucket 1? 2 steps, I'm at bucket 2. 3 steps, I'm at bucket 3. So I want to take index number of steps. What structure do we typically use? What tool do we use if we know exactly how many times we want to repeat something? For loop. All right, so I'll come in here. We'll say node KerrNode is equal to this dot head. So we'll have this guy point to the front of the loop, or point to the front of the list, sorry. Then we'll say for int I is equal to 0, I is less than index, I plus plus, KerrNode is equal to KerrNode dot get next node, and then return KerrNode dot get payload. So that's get at index. Make KerrNode point to the front of the list. Take index number of hops, including possibly 0 hops, right? Because for loops are pre-check loops. So if we fail this right off the bat, if I start off as 0, is 0 less than 0? It's not. So we won't even get into the code one time. KerrNode points to the very front of the list, which is bucket 0. We'll just return whatever KerrNode currently points to, dot get payload. And get payload returns the value that lives in that node. Make sense? All right, so that's get at index. Test that real quick. It's pretty simple, so that should work just fine. So we'll say system.out.println. I'll put how many things am I testing for? 3 asterisks. ll.get at index. We'll go ahead and get it at index 0, 1, and 2. We'll just test the whole thing. And I'm just putting the asterisks before it because that's what I'm filtering on here to make it easier to find. So there's my 273, and there's my display of my entire list. Make sense? So get at index, exhaustively tested. Easy. Okay, what else might we want to do with linked lists? Add middle? Oh, I love that one. That would have been such a fun one for homework, though, wouldn't it? You want me? Oh, you want me to write that one now? Yeah, you're gonna like removes even less. All right, so we're fine. I'll write add middle for you. It's fine. All right, so really what we're doing is we're saying add at index, right? So if I want to add something new at a specific index, what we typically are going to say is we want the new thing we're adding to become that new index. So if I want to say I want to add something at index 2, I would go bucket 0, bucket 1. I need to go right before the index I want this new guy to be. So if I'm adding it bucket 2, I'm going to get to bucket 1 so I can rehook some stuff up. All right. What if I'm adding to bucket 0? Is bucket 0 kind of a special case? Okay, but I don't want to disconnect head yet.
Yeah.
I need the new guy to point to the same thing head points to, and then make head point to the new guy. Okay, so let's write that piece real quick. Where's my link list here? So we'll say public void add at index. This guy will take in a value. Now, we can actually cheat a little bit here. We can say if, we need to take in a value as well as an index here. We can say if index is equal to 0, what can we do? Do I already have something that adds something to bucket 0 of my linked list? Add front. So this dot add front value. So I'm handling that guy as a special case, right? Now, I also could technically handle AddEnd as a special case, couldn't I? If the index is count minus 1, I can just say AddEnd. But I'm not sure that necessarily helps us that much, because adding anything other than the front, we still need to get to the guy right before the guy we're wanting to add it to. I guess we could say if we wanted to become the new end. So if we were adding something, so this guy currently has 4 elements in it, would we be allowed to make the thing we're adding become bucket 4? Effectively, now if we add one more node to this list, we will have 5 total nodes, right? The count will go up by 1 regardless. All right. So technically, we could say we want to actually add this new node at bucket 4. We want him to become the new bucket 4, which means we actually want him to be the new end of the list. That's allowed, right? That would make sense. If somebody wants to add something to a 4-element list and he wants to add it at bucket 4, what he's really saying is I want to add this guy to the end of the list. So how do we ask, are you asking me to add this to the end of the list? Well, I want to be able to ask the question, how do I ask if they want to add to the end? What's the last legal bucket in this linked list? Count minus 1. So that means if adding it to the end means that I'm adding it at bucket count. I want him to become the new bucket count. So I would say else if this dot count is equal to index, then I would say this dot AddEnd value. That make sense? This says I want the guy to be the new end. I want the guy's index to be 1 greater than the last legal index that's already there. The last legal index in this particular list is 3. 0, 1, 2, and 3, right? Those are the legal indexes. But his count is 4. So if I say, if the index you want this guy to be is 4, I'm going to add a brand new node here to the end. He's the new end. Make sense? So lastly, we want to add in the middle somewhere. So what do? We need to run up to the node right before the node we are, right before the location we are setting new node. Good enough. All right, so I'm going to do my usual node KerrNode is equal to this dot head. Start at the front of the list, get ready to start running. How many steps do I need to take? minus 1. I want to go up to, but not including the node. So when we said get at index, if I wanted to get bucket 2 here, I said take, here's 0 steps, that's bucket 0, 1 step, 2 steps. So I'm sitting at bucket 2. If I want my new node to be at bucket 2, I need to actually get myself to bucket 1 so I can hook this guy up in the proper way. Make sense? And how will I hook him up? We'll just go ahead and draw a little picture here. Let's say I'm adding this guy to bucket 2. I'll run up to bucket 1. I'll set this guy to point to the same thing that bucket 1 points to. Then I'll make bucket 1 point to him. And now this is the new bucket 2. But you need to make sure that you do this in the right order. Because if I do those same operations backwards, the first thing I do is I say set bucket 1 to point to the new bucket 2. What did I just do? Lost the rest of my list. Nothing points to this guy. He's going to get garbage collected shortly by the automatic garbage collection system in Java, but punchline for me, I don't have access to him anymore. So it's very important that I do those operations in the right order. So the first thing I do is I connect my new node, make him point to the same thing that the node I'm currently looking at points to. Then I can make the node I'm currently looking at point to my new node. Now I've preserved the integrity of my list, and this guy is now at bucket 2. 0, 1, 2.
How about the KerrNode? Where's it going?
What's the who?
The KerrNode?
We want to go, KerrNode, if we're adding to bucket 2, KerrNode will point at bucket 1. The node right before the index we're adding the new node to. So how do we do that? We have our KerrNode. We're going to say for int I is equal to 0. How many steps do we want to take? Index minus 1, yep. So I is less than index minus 1. I plus plus. KerrNode is equal to KerrNode.getNextNode. So that will sprint KerrNode up to the node that's immediately before the guy we're adding. Make sense? So this is where KerrNode currently points. Now I need to actually build my node that I'm adding. So I'll say node n is equal to new node value. So I have my fresh new node just sitting here pointing out to nowhere. Okay, and that guy's called, if we just want to be completely explicit, this guy's called n. All right, now I want n to point to the same thing that KerrNode points to. So I want to set n's next node equal to KerrNode.get next node. N dot set next node, KerrNode get next node. I'm setting n's next node equal to KerrNode's get next node. Make sense?
So you're in KerrNode right now, it's not pointing to the same.
KerrNode's pointing here. Here's n pointing here. I just set n's next node to be equal to KerrNode.get next node. That's the pointer to this guy. So right now, both n and KerrNode point to the same place. That keeps me from losing the rest of my list. Because now I can just say KerrNode.set next node to n. make sense? And then this dot count plus plus, because I did add something new there. Why didn't I say count plus plus in either of these? It's already in those functions. So you need to be careful, because you might be, for instance, if I would have said, oh, well, I'm adding something somewhere in here. So if I just say count plus plus outside of that whole if statement, if the if structure, that means this line will always happen, right? So the count on my list will be accurate if I got into this else, but my list will be one too large if I got into either of these first two. Because these guys each increment count, and then I'm incrementing count again. So you need to be careful about that. If you're going to keep track of the count in your linked list, make sure you're only incrementing count in the functions that you actually, or in the portions of the functions that you actually added a new node. If you're relying on other functions, let them do that adding. All right, so I'll put that guy back there in the else. All right, so that is add at index. Go ahead and test that. So we already have 3 things here, so we can go ahead and we'll say ll.add at index. We'll add a 13 at index 1. So that'll become the new bucket 1. So we should have a 2, a 13, a 7, a 3 when all is said and done. I'll go ahead and take these get-in indexes out since we've tested that. A 2, a 13, a 7, and a 3. That make sense? And then if I keep testing and just test my add, end, and front, I could say add at index. We'll do a 23 at bucket 0, which we'll call add front internally, and then I'll add a 33 at, so this would be 0, 1. Well, I'm just counting the total number. So 0, 1, 2, 3, 4. So I'm going to add this guy at bucket 4. So he'd be my new end. So we'll have a 33 at the end. $23 there. Was bucket 4 the wrong number? 0, 1, 2, 3, 4. No, it added it to the right place. I need it to be 5. 5 is my actual end there. I counted wrong. There it is at the end. Because there was 5 of these guys before I added my 33. So adding it at bucket count was accurate. I just didn't count right before. All right, questions about that? Okay, so what might be nice is to remove front. I think you'll have a lot more fun writing remove at index yourself. Well, we usually start with the simple cases first, and then we'll run out of time. And then it needs to be done for Tuesday, right? So, I mean, might as well have you work on it for 40 hours. Well, okay, first of all, you're seeing that the code that we have to write for these things is not a great amount of code, right? Really, really, really focus on drawing pictures. It's easy if you draw the pictures. But you need to make sure you understand how you're hooking up these wires, because you don't want this guy to float off into space and stuff like that. Okay? So even you saw in this little example, if we had 2 lines of code and we took those exact 2 lines of code and flip-flopped them, we lost our list. So even order is important. All right? So let's look at remove front. What does remove front say? Remove front says that go ahead.
Can we numbers? Just out of curiosity.
What do you mean get rid of the numbers?
Like, if instead of like, can we just like not have anything point to it in our way of getting rid of it?
Yeah.
Okay.
Yeah, I mean, that's what we will do.
Oh, okay.
Yeah, what he's saying is like, for instance, if I did this, if I disconnected that guy, this guy will get garbage collected. I might want to, maybe as part of the removing, I might want to maybe return the payload of the guy I just removed in case you needed it. You know, maybe you want to get the value at bucket 3 as well as remove him. And if you don't want the value, just don't use it. You know, so it's kind of like a good little tool. You have it if you need it, if you don't. So let's write remove front. Where am I? So we'll say public int. Like I said, we'll go ahead and return the value that we're removing just in case the person who's calling it wants it. Okay? And we'll call this guy remove front. So what are we doing in that case? We'll go ahead and assume that there's at least one element in our list. In this case, we're not going to do error checking. That isn't to say error checking is not important. We're just we're focusing on working with memory here. So don't call remove front on an empty list right now. Doesn't make sense. There's nothing to remove. We'll throw in runtime errors at a later point in time, but just don't call it on the empty list right now. Okay? So remove front says that I want my current front to get disconnected. And I want so I want head to point to whatever head currently points to. And then I want to return the value in this current guy. Now, there is, and this is kind of where automatic garbage collection comes in. And I think this is actually going to be a better answer to your question. If I moved head to point here, this guy will get automatic garbage collected. I like to take the additional step and set his pointer to null. There is an advantage to that. Something only gets garbage collected when its pointer count goes to 0. When the number of things that point to it are 0. So right now, here, I'll just for the sake of what we're actually going to do here, I'll have KerrNode point to the same thing head points to so we don't lose that dude.
You're saying if like you delete both 1 and 2 in indexes,
Then you could have a timing issue.
yeah.
So if I go ahead and I have KerrNode pointing to the same thing head points to, then I make head point here. And I don't disconnect this. Technically, this guy currently has a pointer counter of 1 now. It was 2. When head and KerrNode both pointed to him, his pointer count was 2. When I disconnected head from him, his pointer count went down to 1. When this function ends and KerrNode goes away, it'll go to 0. So he will get garbage collected. But I have artificially left this other pointer to this next node, which won't be a problem once he's garbage collected. But good programming practice would say, we're going to go ahead and disconnect this as well. So this guy is completely free. We'll remove that pointer from our next node because we don't have access to this guy after this function anyways, just in case there's a situation where we try to remove the next guy too quickly and maybe he misses a garbage collection cycle or something like that. Wouldn't be the end of the world, but I'd like to, I guess from a programming perspective, I like to follow the rules of clean up your own messes. All right, something like that. So what we'll do here for remove front is we'll say node KerrNode is equal to this dot head. Then we'll say this dot head is equal to this dot head dot get next node. And we'll say KerrNode dot set next node to null. And then this dot count minus minus. And then we can return KerrNode dot get payload. Make another dude point to the head. have head point to his own next node, completely disconnect KerrNode from the next node. That's cleaning up your own mess thing. You just removed a dude from the list, so we're decrement count. And then, as a good Samaritan, we'll go ahead and return the payload of the guy we just removed, just in case we need him.
Question, do you pull up the pictures there? Okay, so when you put the kernel to null, that means that the kernel is just pointing nowhere. So how did you disconnect the thing to
That's
the
this.
5 to the 2?
This was the order that it happened. So I made KerrNode point to the same thing as head. Okay, we're good with that part.
Mm-hmm.
Then I made head point to his own next node. Then I set KerrNode's next node. KerrNode points to here, to null.
Oh, okay. So go that way.
Yep, that's the move right here.
That makes sense.
All right, so I assume you're good. You don't want me to push this code up? Pass around the collection. Pass around the collection plate. All right. So for Tuesday, remove end and remove at index. All right. We will have our midterm on Thursday. We'll talk about it on Tuesday. It's standard, 10 questions. Several of them will be programming. Some of them won't be. If you do better in your final exam, you do in your midterm, I'll replace it. So normal Lippmann test thing, right? All right, I'll go ahead and push this and put the assignment up, and I will see everybody on Tuesday. Hopefully I see several of you tonight in the fishbowl to watch Hidden Figures with myself and the rest of the Grace group. Big prizes. I think we're giving away a motorbike and an iPad. Show up anyways. Giving away a car.
What did you say the assignment was? Is it add or remove and?
Remove and remove an index.
Remove index.
Huh?